Okay, thank you, Tao, for this nice introduction. And I am grateful for this opportunity to be able to present my work. And I thank everyone for attending this talk. So I want to start by some examples of smart infrastructure network systems. And one of the examples is transportation networks, where we have certain autonomous vehicles that might be communicating with each other. There's a autonomous bus, and they might also be communicating with some humans who might be wearing some smart wearable devices. There are also some smart infrastructures such as this smart lamps, smart parking meters, and all of these smart systems are communicating with each other. But two or three points to note here is that there is some interconnected structure, and there might be some AI agents on these individual systems that are responsible for high-level planning. And each of these systems, for example, this car or this parking meter, might be of high degree of freedom. Right? Now, the other example is of smart grids, where the subsystems here can be a thermal power plant, a solar plant, even smart houses. And again, smart houses can have some AI agents running, which might be responsible for demand response programs. And again, we have some interconnected structure, and all of these subsystems are, again, can be of high degree of freedom. So if I try to simplify these images, the image on the right is one way to depict these smart infrastructure systems, where on the lower level, we have these subsystems, Sigma F1, Sigma F2, and so on. And to go back to the example, the Sigma F1, Sigma F2 can represent our autonomous vehicles or the power plants or smart houses. And these subsystems have some low-level controllers that are responsible for low-level controls. And they might also have some AI agents that are responsible for high-level decision making. And for this talk, by AI agent, I mean that these are some software systems that are responsible for decision making, and they may have some learning component that they are incorporated in them to improve performance. There might also be some human agents that might be interacting with these AI agents, and these AI agents might also be interacting among each other. And the last thing to note here is that there might be some disturbances acting on these subsystems, right? And for this talk, use this word disturbance pretty loosely, in the sense that it can modeling errors or attack on these systems. It does not only have to mean some environmental uncertainty. Okay. So I would claim that the modeling these smart infrastructure systems is critical. And the reason is that we need these models to understand the behavior of the system. We want to be able to do what if scenarios. And what this means is that I want to understand, if an attack happens on my system, how will the system behave? How can I prevent that attack, and so on? I want to be able to use these models for capacity planning, which means, for example, in a smart transportation network, there can be days when a highway is congested because a lot of people or cars decided to take that highway. So a smart transportation network should be able to reroute some of the vehicles to take another highway. And finally, we can use these models for real-time monitoring and control. And on the right, I'm showing some of or two examples where these models or digital twins have been used for for at least some of these points that I just discussed. For example, in Norway, a digital twin of a bridge was used for monitoring the structural integrity of the bridge. And similarly, in Japan, digital twin is being used for what if scenario to understand or model the behavior of the city under disasters. Okay, but the challenge here is that if we model these systems with the same complexity as the true system, then they are going to be very resource expensive. And for your reference, one simulation of a smart building can take 1 to 2 days. And this is based on a talk that I attended by PNNL. So now you can imagine, if one simulation of smart building can take 1 to 2 days, simulating an entire city, such as in this for this digital twin in Japan, can take a long time. So one idea to address this challenge is that I club all of these subsystems together and I reduce it into a single system. And then I might have to design a new controller, because I can't use the same controller as the system is different. And I might now also have to design a new AI agent, which is a reflection of all these AI agents combined together, right? So you can imagine that this becomes complicated, but one of the problem in doing so is that even in the lower level, the interconnection structure is lost, right? And why this is a problem is because suppose there is an attack that happens on subsystem one, or maybe a disturbance attacks only on system one. Then if I'm using a digital twin and I'm looking at this simulation model to look at the behavior of this true system, then all I will see is that the behavior has changed, but I will not be able to see that the behavior has changed due to this subsystem, right? So then I cannot actually see how an attack on this subsystem affects this overall system. So that's the reason we want to preserve an interconnection structure. So now another classical idea that has been proposed in the literature is that we can reduce these smart stress systems or these systems in the lower level in a modular manner. And what that means is that I individually reduce these subsystems. So the sigma R1 is a subsystem as a approximate subsystem of sigma F1, sigma R2 is an approximation of sigma F2, and so on. And then I interconnect them using the same interconnection structure as this one, right? So now, as you can imagine, that doing this preserves the interconnection structure. And I can now design individual controllers of these subsystems. And that I can use to ultimately control these true systems. And this is where the data sharing comes in, that I design a controller, CR1, based on the reduced systems, sigma R1, and then I can share that input signal to control this system, sigma F1, right? So but if we look at the AI agents, the good thing is that now I can just use the same AI agents as the true system, and I don't have to deal with designing different AI agents, right? Now, one thing to note here is that if I want to design a controller for these reduced system, which ultimately controls this true system, then my approximation system, sigma R1, must behave similar to this sigma F1, even under the presence of disturbance. What that means is that if a disturbance D changes the behavior of that system sigma of 1, then the behavior of sigma 1 should reflect that change in the system. And that is a property that I call as robustly approximate. And we'll see some examples later on what I mean exactly by this. Okay. So with this idea, there are many questions that start arising. If we look at the lower level, then there are questions regarding reduced order modeling that one can ask. Now, one of the questions is, how do we reduce these sigma F1 or sigma F2 into sigma R1, sigma R2? Are these reduced models good, and what are their fidelities? And we can also ask questions related to robustness. Okay. In the upper level, we can start asking questions about robustness of these interaction among agents. We can ask, what if an AI agent is adversarial? And looking at the middle sector, which is the sharing of the data, we can start asking question, which data to share among the simulation or a reduced system and the true system, when to share that data. And given the complexity or the scale of these systems, can we design efficient algorithms for identification and control of these systems, right? So these are the questions that I've asked and answered in the past couple of years. And for today's talk, I will only be focusing on the first part, which is the reduced order modeling, and the second part, which is robust interaction among agents. The third part I will not talk today, but in the end, I will probably spend a minute just to talk about what I have done in this area as well. So, by the way, the part one is in collaboration with Professor Caroline Beck, who is in UIUC, and my advisor, Vijay Gupta. Okay, so let me start by part one, and I'll start with an overview of model order reduction. So the idea behind model order reduction is that if I have a dynamical system of very high order, I want to be able to approximate it with the lower order system such that the outputs of the two systems are similar. Okay? Now, for this talk, I will focus on linear systems. And for linear systems, there are many methods available. One method is balanced truncation, and the second method is moment matching. If you don't know these methods, that's okay. For this talk, you don't need to know these methods. All you have to keep in mind is that there are these two classical methods that exist for model order reduction of dynamical systems. Okay. Now, to make this definition or this process of model order reduction a little bit more formal, I have I'm introducing a little bit of math here, that I have a system sigma F of order n, and the system sigma F is characterized by matrices A, B, C. I apply a model order reduction on this system, some method for model order reduction on this system, and I obtain a system sigma R, which is of order R, which is much less than n. And the system sigma R is characterized by matrices AR, BR, CR. Now, this method that I use for model order reduction must be such that the error between the outputs, the norm, must be small. And by small, what I mean here is, if we look at the plot on the right, the blue curve depicts the output of the system sigma F, and the red curve depicts the output of system sigma R. And we can see that the output of the two systems are very close to each other. And in fact, if I plot the error is small. So that's the whole idea behind model order reduction. Okay. Now, one of the application for just model order reduction is in semiconductors. In fact, Purdue is now leading digital twin institute for semiconductors. And for any method of model order reduction, there are certain properties that are desirable. So one of the properties is that we want theoretical bounds on the performance. And by performance, I mean the error between the outputs. We want that our reduced order model should be able to preserve stability. What this means is that if my original system or true system is known to be stable, then I want my reduced model to be stable as well. I want the framework to be computationally inexpensive. I want some compositionality properties to hold, and I want the reduced model to be robust. In robustness, I have two points. One is the robustness to disturbances, which is in the classical sense. And the second is the property which I spoke about in 2 or 3 slides back, which is robustly approximate, which means that the performance of the reduced model should be similar to the true model, even in the presence of disturbances. And finally, we want some closed loop properties of the from the reduced order model. Now recall that there are two classical methods, balance truncation and moment matching, that exist out there. Now, and balance truncation out of these 6 properties satisfies the first 2 properties, and moment matching satisfies the third property. Now, I want to highlight here is that I'm not claiming that these methods are bad because they only satisfy 2 or 1 property. In fact, I want to claim otherwise, that, and even in the literature, it is even by satisfying these 2 properties or 1 property, these methods has been regarded very well in the literature, and I'm not claiming otherwise. Okay. Now, I want to motivate my talk by giving one example on how these classical methods perform when some disturbance acts on the true system. Okay. So suppose a reduced order model is obtained via moment matching. Remember, moment matching is a classical method that exists out there. So I have a linear system characterized by matrices ABC. I apply moment matching and I obtain a reduced model AR, BR, CR. And on the right, I'm plotting the performance of the true system and the reduced system. And the performance is decent. It's a nice performance. But what if a disturbance D acts on the true system? So if I apply a disturbance D on the true system, the performance of the true system, instead of this blue curve, now is the black curve. But now here we see that the performance of the reduced model, which was the red curve, does not really follow the black curve. Okay. Now one can say that why can't I consider the disturbance as a second input and then apply moment matching? Well, that will require the disturbance to be known, which is not really the case in real life scenarios. And one can do the same thing with balance truncation, but the idea here is that these existing methods are not robustly approximate. And by robustly approximate, again, what I mean is that this red curve should follow the black curve. And that is intuitively saying that even under the presence of disturbances, my reduced model should be following the performance of the full order system. Okay. Okay, so to address this, the main idea behind our work is that if we are given a true system sigma f with input uf, output yf, and some disturbance d acting on the system, I want to be able to construct a reduced model sigma r and a perturbation input upert, such that now the output yr of my reduced system is similar to the output of the full order system. Now, this idea is not mine. It is based on a recent work, which I am citing it in the at the bottom of the screen. which belongs to this long line of bi-simulation literature, which started in theoretical computer science, and it was brought into control, I believe, by George Papas in early 2000s. Okay, but I will be focusing on this, or our idea is based on this paper into 2024, which is on the gamma delta similar systems. And what that paper suggests is that a system sigma f is gamma delta similar to sigma r if for some given positive constants gamma and delta, there exists a perturbation input in the class of L2 such that the signals, these inputs to the two systems UF and UR, and the disturbance, which are in the class of L2, and for all of these signals, the output is bounded. And by bounded, what I mean is that the norm between these outputs is less than this expression on the right. Okay. And now if we look at in each of these individual expressions, the first part in this expression corresponds to or characterizes the dissimilarity in the inputs to the two systems. And one can imagine if the input is the same to the two systems, this term is 0. The second part or the second term corresponds to the effect of each input that affects the error between the outputs. And finally, the third term is characterizing the effect of disturbance that affects the error between the outputs. And these gamma, delta, and mu are some constants. Now, one thing to note here is that this bound that I have is independent of the order of the two systems. And so that's the intuition of why we are able to use this framework for model order reduction. And the second thing to note here is that if I want to use this framework for model order reduction, I want this right-hand side to be as small as possible. And the way one way to achieve that is I can minimize these constants, gamma, delta, and so on. And that's what we do in our work. So in our work, we propose a method to design gamma delta reduced order models based on this concept of gamma delta similarity. And the way we do so is they come up with an optimization problem where we are minimizing the constants gamma and delta. And we are also minimizing this problem over these matrices AR, BR, CR, which characterizes the reduced model. And then there are these additional optimization variables, X and pi, which basically characterize my perturbation signal of that is applied to the reduced order model. Okay. So if I can solve this optimization problem, then I can say, then we can obtain a gamma delta reduced order model. Now, one thing here is that this inequality is a bilinear matrix inequality. And I think after a couple of slides, I will talk about how we can reduce this into a linear matrix inequality. And for this talk, I will denote this optimization problem as P0. By the way, these matrices A, B, and so on are just determined based on the composite system of the two systems, AF, the full order system and the reduced order system. And on the bottom, I have the mathematical descriptions if you want to see. Okay, so now once we have the framework of that helps us determine gamma delta reduced order model, I want to talk about the properties that this framework satisfies. So right off the bat, we can say that the gamma delta reduced order models are robustly approximate, and recall robustly approximate means that now the reduced model will follow or will approximate the output of the true system even under the presence of disturbances, right? And the second point here is that we have an analytical error bound where this gamma min and delta min are the solution of the optimization problem. Okay. The third property is that we can show is that these reduced models that we construct through our framework are also asymptotically stable if the true system is asymptotically stable. So we have this preservation of stability property as well. Now, before I proceed further, here's a numerical example to clearly illustrate the robustly approximate property of framework. So earlier I had an example where I was using moment matching, which is one of the classical methods in the literature, to reduce a given system. And under the presence of disturbances, what we saw was that the performance of the reduced model, which is this red curve, does not follow the black curve. However, in our framework, we see that this red curve starts following the black curve. And that is what I mean by robustly approximate. And the reason we want this property is that because remember, I want to be able to design controllers using the reduced order model for the full order system. Okay, so if we go back a little bit, I had talked about some desirable properties from model order reduction method, from any model order reduction methods. And out of those 6 properties, until now, what I've talked about is that we are able to satisfy the first 2 properties. And in robustness, we are also able to satisfy the second property in the robustness, which is the robustly approximate. Now, the question is, does our framework satisfy other desirable properties as well? And fortunately, the answer is yes. But before I talk about how we satisfy those properties, let me go back to the point where this constraint was a bilinear matrix inequality and how we can reduce it down to a linear matrix inequality. The way we can do that is we can combine this framework, gamma delta model order reduction, with any existing reduced order model method out there. So for example, I can use balanced truncation or moment matching to obtain a reduced order model. And then the optimization problem, since AR, BR, CR are now given, the optimization problem reduces down to finding the disturbance and minimizing these constants such that this inequality holds. And now this constraint becomes an LMI. The benefit here is that LMI are computationally easier to solve. So that's one benefit that our framework gets by combining this framework with existing methods. But this benefit goes both ways in the sense that now the existing methods can also enjoy these properties that our framework has. So for example, moment matching is not known to have an error bound, but if it is combined with our framework, now it can have an error bound and so on. Okay. Okay, so now let's go back to what other properties that a framework satisfies. And I will start by talking about compositionality properties. And I want to spend a minute or so just motivating why coming up with error bounds on arbitrary interconnected systems can be hard. So for an example, consider a system sigma f, which is an interconnected system between two systems, sigma 1 and sigma 2. Each sigma 1 and sigma 2 is of high degree of freedom. And they're connected through an interconnection structure. This U1 and U2 are some external inputs, and Y1 and Y2 are some external outputs, and W and Z denotes the internal signals in this system. Now, using any existing method, I can reduce this reduce the system in a modular manner, meaning that I can construct sigma 1R, which is an approximate system of sigma 1, and sigma 2R is a reduced approximate system of sigma 2, and I'm connecting them in the same same interconnected structure. Now, because sigma 1R and sigma 2R are not exactly, their outputs are not exactly the same as sigma 1, there are some approximation errors. Due to this interconnection structure, these approximation errors start accumulating over time. And that is one of the challenges in coming up with error bounds for interconnected systems. The way we address this in our framework is that we say that instead we reduce these systems using our gamma delta reduced order model method, and that is why I now have these perturbation signals acting on these two systems. And now once I obtain these sigma 1R, sigma 2R, I'm connecting them in the same interconnected structure as the true system. And once we do this, what we can show is that for any arbitrary interconnected structure of a composite system of n systems, so in this example, I'm considering n equal to 2, but the result holds for any n, we have an analytical error bound between the error of the external outputs of the system. And the error bound is again given by this right-hand side of this expression, where the first part again characterizes the effect of disturbance. Now, recall that this gamma delta, which are the constants that are obtained from an optimization problem. So these gamma and delta values are supposed to be small, and this delta max is the maximum of those delta values that I get. Okay, so that's what delta max is. The third term in this expression corresponds to the dissimilarity in the external outputs. And again, if my external outputs are the same, this term is 0. And finally, the fourth term characterizes the effect of each external input to these two systems, sigma f and sigma r. Okay, so I know this slide is a little heavy. So as a summary, the compositionality property that we have in our paper is that by reducing interconnected high order system in a modular manner using our framework, which means that design these reduced order model using gamma delta reduced order model framework, uh, which are corresponding to the sigma 1, sigma 2, and so on. And if I connect them in the same interconnected structure, what we are able to show is error bounds for arbitrary interconnected structure. And for special connections such as feedback, cascade, and parallel, we have stronger error bounds or tighter error bounds in our paper. Okay. So now let's look at what closed loop properties can one satisfy using this method or gamma delta similarity. Now, and I will do that. I will show these or illustrate these properties using two examples. So one of the application that I will talk about right now is controller design. So the idea here is that if I have a system sigma f and there is some disturbance df acting on it, I design a reduced model sigma r using our framework, and here's the perturbation signal that acts on it. And then I design a controller based on this reduced order model. Okay. And then the idea is that I want to apply the same controller to this true system. One can do it in multiple ways. One is that I send this UR through a communication channel to the system, and that's what this sharing of data illustrates. Or the other is that I can apply the same controller to the true system. Now, one thing to keep in mind is that if an application is of designing these simulated models as a digital twin, meaning that even this simulation model is a physical system, then I want this reduced model to be robustly approximate in the sense that because I'm designing or I'm using this system to design a controller, this system's behavior or output should be similar to the output of this system, even under the presence of disturbance. Okay? And what we are able to show is that if we design controller and apply it to the original system, then we can ensure closed loop stability of the true system by designing controllers on the reduced model. And here's an example of a spring mass damper system where the red dash curve is the output of the closed loop full order system, and the black curve is the output of the closed loop reduced order model. For the full order model, the control is applied using the controller designed on the reduced model. And the blue curve is, if I follow the same process with balanced truncation, but here we see that balanced truncation, when I apply a disturbance at time 10, it does not follow the output of the true system, whereas our framework does. Okay. Now, a second application that one can consider when using reduced order models for control is robust control of full order models. And I will describe that as an implicit control framework. What that means is that if I have a system sigma f, there is a disturbance affecting the true system sigma f. And then I can design a reduced order model sigma r. And now I want my system sigma f to be gamma delta similar to the reduced system sigma r. Okay. And that's the difference between the previous application and this application. But the controller is again designed using the simulated reduced order model. And once the control signal is determined, we send that control signal to the true system. Now here, the one thing to note here is that this approximate system is not a physical system, but it's a simulation, which is in the implicit in the true system. So I do not want my reduced model to be robustly approximate. In fact, I want my reduced model to be robust. And by the way, the contents on this slide are recent works, which will be coming out soon. So stay tuned. But what we are now able to show is that by using reduced order models in this framework and combining it with gamma delta similarity, we can now do robust control of original system for any disturbance in the class of L2. And we can now apply it to various applications such as linear quadratic tracking, MPC control barrier functions. And here's an example of constant reference tracking that we have considered. So in this example, I want my full order system to follow a constant reference at 1. So the red curve here shows the output of the reduced model. And since I designed the controller based on the reduced model, we see that the performance is really nice. And when I apply the same controller back to the true system, the true system is following the constant trajectory, except at a point at time instant 10. And there's a small bump, and this is because at time 10, I apply a disturbance of magnitude, I believe 15. And this small bump corresponds to the approximation error that is coming from the reduced model and the true model, right? So there's some robustness going on here. And as a comparison, if our process is not used, the bottom curve shows that without our framework, the closed loop system might not even be stable. So the tracking performance is definitely not achieved. Okay, so this brings me to the close of my first part of the talk, where I focused on this lower level and I answered questions on how do we reduce these individual subsystems. I answered the question on the fidelity, and I also addressed the robustness issues and these reduced order modeling part. Now I want to shift my focus to the upper level, where I want to talk about these interaction among agents, and specifically, I want to address the robustness aspect of these interactions. And by robustness, what I mean is that in smart infrastructure system, these AI agents can be adversarial in nature, right? Now, for the sake of this talk, I will not be considering the presence of human. I will only be focusing on the presence of AI agents. And as I would like to highlight that this second part of the talk is in collaboration with Professor Yinei Vorobechik, who is in Washington University in St. Louis, Pranoy, who is a PhD student in our group, and my advisor, Vijay Gupta. Okay. So when I talk about interaction among agents, the literature that comes to at least my mind is game theory, and that is because it gives a very nice framework to model interaction among agents. So as an overview, I can represent an interaction among the agents as a matrix game. And on the right, I'm showing an example of a game of rock, paper, scissors. The rows and the columns represent the actions of the agent. So rock, paper, scissors, rock, paper, scissors. And the entries correspond to the reward that an agent gets depending on the or corresponding to the action chosen by the agent. So for example, if both agents choose rock, then they both get a reward of 0. If agent 1 chooses a reward, chooses an action rock, and agent 2 chooses an action paper, then agent 1 gets a reward of -1, and agent 2 gets a reward of 1. Okay. Now a strategy, which I will be denoting as pi, is a probability distribution over the action set. And Nash equilibrium is a pair of equilibrium strategies such that no agent has unilateral incentive to deviate from its Nash equilibrium strategy. Okay. So, okay. So there are cases when we might not know the payoffs of the games. And in that case, there is a classical line of literature called learning in games, where the idea is that the matrix game is repeated over time to learn the Nash equilibria. And there are many algorithms that have been designed in this literature. The desiderata from these algorithms is that if an opponent is playing a fixed strategy, then we want to learn an optimal policy against it or an optimal strategy against it. If the opponent is also learning, then we want to keep adapting our strategy such that the strategies reach a steady state of mutual best response. And again, many algorithms exist. Two of the examples would be fictitious play or regret matching. And if you don't know these algorithms, that's okay. For this talk, you don't need to know these algorithms. All you have to keep in mind is that there are these classical algorithms that exist out there for these in this literature of learning in games. Now, almost every algorithm in the literature has a result of the kind that if every agent follows the same algorithm, then under certain assumptions, the algorithm converges to an equilibrium. So an example of this would be if every agent follows fictitious play is one of a classical algorithm, then under assumptions such as a two-player zero-sum game, fictitious play converges to a Nash equilibrium. Okay. Now I want to spend a few seconds or a minute in this result, where this result is a double-edged sword for smart infrastructure systems, in the sense that this requirement of having every agent running the same algorithm is advantageous because I don't need to worry about different algorithms run by different agents. But a disadvantage is that since these agents are strategic in nature, they are self-interested, they can deviate to any other algorithm, or they shouldn't be restricted to follow the same algorithm. And this deviation might not be detected in time, and that can lead to unforeseen circumstances. So here's a plot to highlight that disadvantage or motivate my framework. So this plot represents the payoff of an agent, and the blue curve denotes the payoff of an agent, or in this case, I'm calling it adversary. If the adversary follows the same algorithm as every other agent, then the blue curve denotes its payoff, and we can see that it converges to 9 over time. But if the agent is adversarial in nature, it can exploit the fact that every other agent is running the same algorithm, and it can deviate to some other algorithm, and it can obtain a higher reward. So here we can see that because it can obtain a higher reward by deviating to another algorithm, it has some incentive to deviate to another algorithm, right? So the idea behind our work is that we want to be able to design robust learning algorithms that ensure that agents do not deviate to any other algorithm. And because I've used robust in the previous part as well, I want to clarify that by robustness, I mean that the algorithms should be such that the agents should not have any incentive to deviate to another algorithm. And the approach that we take in our paper is that we view the choice of algorithms as strategies. Okay. And what that means is that we want the agents to be able to select any arbitrary algorithm that they want. Now, if we focus on this robustness property, since I want my algorithms to be robust in the sense that the agent should not have any incentive to deviate, the first question that comes to mind is how do we even characterize incentives for deviation? So that's one of our starting point, that in our paper, what we do is we introduce this metric called rationality ratio to quantify the incentive for an agent to deviate from an algorithm. Okay, and this rationality ratio is defined as follows. So if I denote rationality ratio with the letter S, it's a fraction between the payoff of the same agent. So in this example, I'm considering agent 1. And in the numerator, it's the payoff of agent 1 for a game G when agent 1 follows algorithm A prime and every other agent follows algorithm A. Okay. In the denominator, I have the payoff for the same agent and for the same game, but now the agent 1 follows the same algorithm as every other agent. Now you can imagine if this fraction is greater than 1, then that means that agent 1 has certain incentive to deviate to algorithm A prime. Whereas on the other hand, if this fraction is less than 1, then that means that this agent does not have an incentive to deviate to algorithm A prime as compared to algorithm A. Okay, so with this rationality ratio definition, we say that an algorithm A is C rational if for every game G and every algorithm A prime, this fraction can be bounded by a constant C for any constant C greater than 1. And I call this algorithm perfectly rational if C is equal to 1. And intuitively, perfectly rational algorithm means that any agent does not have any incentive to deviate to any algorithm. And a nice property of this metric is that this metric provides constant factor guarantees to the algorithms as opposed to some other metrics which are additive in nature and that can scale with the rewards of the game. Okay. Okay, so once we have this metric, what we want to understand is our existing algorithms, such as fictitious play and regret matching, which have been proposed in the literature, are they C-rational or not? And what we are able to show is that fictitious play algorithm is not C-rational for any constant C. And intuitively, what that means is that if every agent is following fictitious play algorithm, then an adversarial agent has an unbounded incentive to deviate to another algorithm. Okay. And we can show the same result for regret matching. Now, one thing I would like to highlight here is that regret matching is known to be no regret algorithm. A no regret algorithm is one in which if let's say agent 1 is playing regret matching and agent 2 is playing some other algorithm, then agent 1 will not have any regret. Now, this result, what it implies is that even no regret algorithms may not be C rational, or in other words, even no regret algorithms even against no regret algorithms, agents might have unbounded incentives to deviate to another algorithm. And intuitively, or one of the implication of this is that regret might not be a good metric to quantify incentives for deviation for an agent. Okay. Now, once we have these negative results, the next thing we wanted to understand was under what information setting do these algorithms exist? So I will be considering two information settings in this talk. The first setting is perfect monitoring. And what this means is that in perfect monitoring setting, every agent observes the actions as well as the payoffs of every other agent. Okay. Imperfect monitoring setting, on the other hand, is the one in which every agent observes the actions but not the payoffs of the other agents. And what we are able to establish in our work is that under imperfect monitoring, there are classes of gains in which these algorithms do not exist. Okay? So basically, if an agent is not able to observe the payoff of the other agents, then designing these algorithms is very hard. Okay, so this is another negative result. And given these negative results, the question is, do these rational algorithms even exist? And fortunately, the answer is yes. And now I will talk about how we can design these algorithms. So the setup that I will be considering in the remainder of this talk is that I will be considering a two-agent game in a repeated setting. And this is just for ease of exposition. This can be easily generalized to n agents. I will consider that the agents do not know the payoffs in the start. And I will assume perfect monitoring. Recall, perfect monitoring is the one in which every agent can observe the action and the payoff of every other agent. And for the value or the reward, I will consider the long-term average reward obtained by an agent. Okay. So here's the framework that we propose in our work. So our framework requires an existing algorithm A as an input. This A can be fictitious play or regret matching or any other algorithm that exists out there. The agents start in an exploration phase where the idea is that the agents will maintain and update the estimate of the payoff matrix of the other agent. Recall that I consider that the agents do not know the payoffs of the other agent. So that's why they start in the exploration phase. And after a certain time interval, every agent will check if the other agent has deviated from the algorithm or not. Okay, if not, and if the payoffs are still not known, they go back to this exploration phase and this continues. Now, suppose if the payoffs are known by the agents, they enter the exploitation phase, where the idea is that the agents will choose the actions based on the algorithm which was given an input. So for example, if as an input fictitious play uh, was given, then the agents will choose actions according to fictitious play in this exploitation phase. And again, after certain time interval, they will check if the deviation has occurred or not. If not, they go back to the exploitation phase. Now, either in exploration or in exploitation phase, if a deviation is detected by an agent, then the agents enter a punishment phase where the idea is that the agents who have not deviated from the algorithm punish the agent who has deviated by playing a minimax strategy against it. The challenge here is that if an agent deviates in an exploration phase, how do we punish or how do we compute this minimax strategy when we don't even know the payoff of the other agent, right? And the second thing is, how do we detect a deviation has occurred or not? So I'll start by addressing the punishment phase challenges. So recall in the exploitation phase, the payoff matrices are known. So if an adversarial agent deviates in the exploitation phase, then, and since I'm, for ease of exposition, since I'm considering agent one and agent two, I'm so assuming agent two deviates. So then agent one can just use a minimax strategy over agent two's payoff matrix and play the minimax strategy against it. In the exploration phase, since the payoff matrix is not known, the idea is to construct a virtual payoff matrix for agent 2. And we do that by replacing all of the unknown entries with 0, and then we determine a minimax strategy against it. And whenever an entry of that matrix is revealed, we update it with 0. Otherwise, we keep it 0 until it is revealed, or it might not be revealed. And with this idea, what we are able to establish is that any algorithm that incorporates this punishment phase can be converted, is actually a C-rational algorithm as long as this condition holds. And intuitively, what this condition means is that the minimax value that is obtained by the adversary must be sufficiently low, right? And another intuitive explanation here is that the punishment should be effective for the adversary. Now, this is good because I am saying that if I incorporate this punishment phase, any algorithm is a C-rational algorithm. But to enter this phase, we must be able to detect a deviation, and that's what I will be talking about next. Now, if the algorithms are deterministic in nature, then checking for deviation is simple. But most of the algorithms in the literature, they are stochastic in the sense that the agents choose action based on some probabilistic rule. So our idea is that every agent constructs two copies of a distribution. One copy corresponds to the distribution for the agent that it must have chosen the action from. And the second copy corresponds to the distribution that the agent actually chooses its action from. Okay, and then after every NT time instance, every agent will check this difference. If this difference is greater than certain threshold epsilon, then we say that deviation has occurred. And these parameters nt and epsilon t are dynamic, so basically they're changing with time. And in this slides, I'm not actually talking about how we design these parameters, but they are suitably designed to ensure convergence to an equilibrium, right? So with this framework, our main result is that given an algorithm A, which is an input to our framework, suppose pi1 star and pi2 star are the equilibrium strategies of that algorithm. Okay. And now using our framework, if I design a rational A algorithm, and if I denote phi1 star and phi2 star as the strategies of that rational A algorithm, then I can ensure that this rational A algorithm is C rational with for a given constant C. And we also ensure guarantees convergence to equilibrium with high probability. Okay, so we are ensuring robustness without really jeopardizing or trading off the guarantees to convergence. So that's the main idea behind this result. Okay, so as a numerical illustration, I consider fictitious play as the example, and this blue curve denotes the payoff for agent one when every agent is following this fictitious play, which has been proposed in the literature. Okay, and the red curve shows that if every agent follows fictitious play, then an adversarial agent, if we consider agent one to be adversary, it can deviate to another algorithm to get a higher payoff, right? So that is showing that fictitious play is not robust. And now if we consider our framework, which gives us rational fictitious play algorithm, and if an agent or the same adversarial agent deviates during exploitation payoff, now we see that the reward, this yellow curve, is less than the blue curve, which means that now the adversary does not have an incentive to deviate from this algorithm. Similarly, we can show that if agent one deviates from the exploration phase, which is when the payoff matrices are not known, again, the purple curve is below the blue curve. So that means that the agent will not have any incentive to deviate to any other algorithm. So the bottom line here is that our framework ensures that no agent has any incentive to deviate to other algorithms. So this brings me to the conclusion of my talk. I spoke about model order reduction in part one, where I discussed where I presented a framework for model order reduction, and I discussed multiple theoretical guarantees that our framework satisfies. In the second part of the talk, I considered interaction among agents, and I introduced rationality ratio metric. I also gave some fundamental limits on the existence of C rational algorithms, and I also presented a work or a framework to design such algorithms. Here are the QR code of these papers that you can scan if you're interested in reading more about these works. Now, I want to just conclude by going back to the big picture, where recall I had a illustration of a smart infrastructure system or a large scale complex system on the left-hand side. And on the right-hand side was one way that I can construct a model or a reduced model that can be used for various purposes, such as what if planning and capacity planning and so on. Right. And earlier I had talked about some answered questions or the questions that I have answered in the couple of years. And I had said that I will not be talking about this third part. I want to spend probably 15 seconds or so just to highlight what I have been doing in this area. So in the third part of my research, I've been asking questions such as which data to share and when. And I've been addressing this question by designing event-triggered reinforcement learning algorithm. And for the question related to efficient algorithms for identification and control, we've been looking into transfer learning approaches under large heterogeneity. Okay. Now, some questions that I have not answered yet, and I'm very interested in answering, is that what happens if the agents or these AI agents do not have perfect monitoring or do not observe the payoff, or if the information among the agents is asymmetric, right? And in the lower level, one of the questions that I am interested in answering is, what if we do not know the interconnected structure of these systems? So until now, I've been assuming that we know the structure, and that is how I'm able to connect these reduced systems with the same interconnected structure. But one thing that I would like to address is, what if this interconnected structure is not known? So with this, I would like to conclude my talk, and I would like to open the floor for questions. And thank you again, everyone, for attending this talk. So, yeah.